Let us now discuss the autonomic nervous system neurotransmitters and receptors. Major neurotransmitters of autonomic nervous system are acetylcholine and norepinephrine. Now, acetylcholine is used by both systems, sympathetic and parasympathetic, and it's released by cholinergic fibers, which are basically all autonomic nervous system preganglionic axons and all parasympathetic postganglionic axons. Now, what differs here then is the norepinephrine released by adrenergic fibers, which are almost all sympathetic postganglionic axons except those at sweat glands. So the effects of neurotransmitter depends on whether it binds to cholinergic fibers or adrenergic fibers. So there are two types of cholinergic receptors. We have here the nicotinic receptors and muscarinic receptors. So the first is nicotine or binds nicotinic receptors and mimics the effects of acetylcholine. And muscarinic receptors are sensitive to muscarine, which is actually a mushroom poison. Now, the nicotinic receptors is found on all postganglionic neurons, which are the sympathetic and parasympathetic. They are also found in the hormone-producing cells of adrenal medulla and sarcolemma of skeletal muscle cells at neuromuscular junction. And the effect of acetylcholine at the level of nicotinic receptors is always stimulatory because, as we've learned, nicotinic receptors were legated on ion channels that can allow for an influx of sodium that is depolarizing and therefore excitatory post-step potential. So the acetylcholine interact with the nicotinic receptor and it's gonna open its ion channel and depolarize, and therefore it's always stimulatory. But that's only if it's a nicotinic receptor. So this is different to muscarinic receptor because it is first of all found on all effector cells stimulated by postganglionic cholinergic fibers. So mostly the parasympathetic nervous system, but some little bit of the sympathetic nervous system with sweat glands. In the effect of acetylcholine on muscarinic receptors, it is different because it can either be excitatory or inhibitory. It depends on a receptor type of target organ. So when acetylcholine binds to cardiac muscle cells, it actually slows down heart rate, and this differs than when acetylcholine binds to muscarinic receptors on intestinal smooth muscle cells because this actually increases the rate of contraction. So for the adrenergic receptors, these are actually sensitive to noradrenaline, adrenaline, or as called norepinephrine, epinephrine. And there's two subclasses. We have alpha and beta adrenergic receptors. So alpha 1 and 2 and beta 1, 2, and 3. Now, the effects of norepinephrine and epinephrine on these receptors really just depend on the receptor that predominates on the target organ. So when norepinephrine binds to cardiac muscle beta 1 receptors, it causes increase in rate. But when epinephrine binds to bronchial smooth muscle, it actually causes to relax because of these beta 2 receptors. So it ultimately depends to the type of receptor that helps determine the response on that organ. So this is extremely important to know because a lot of pharmaceutical drugs actually target these receptor types to, have an effect from the body. So for instance, for individuals who have anxiety and high blood pressure, you can give them a beta blocker like propranolol that can actually inhibit beta 1 receptors. So if you prevent beta 1 receptors from being activated, then you don't get any increase for heart rates or force force of contraction. So if you have high blood pressure, taking propranolol that inhibits beta-1 receptors would actually decrease heart rate and force of contraction because you're not able to stimulate these receptors. And in that regard, it can actually help you feel more calm. So this is the summary of the cholinergic and adrenergic receptors. Remember that cholinergic are nicotinic and muscarinic receptors, and they are called cholinergic because they are both sensitive to acetylcholine. Now, nicotinic receptors are always excitatory because they are ligand-gated ion channel and that they generate excitatory postsynaptic potential. And these nicotinic receptors is found in all postganglionic neurons, adrenal medulla cells, and neuromuscular junctions of skeletal muscle. Muscarinic receptors are found on all parasympathetic target organs, and although they're mostly excitatory, there are some cases of inhibition as well, like with cardiac muscle. And we also find some muscarinic receptors on sympathetic targets like the eccrine, sweat gland, and these are also activated that increases the rate of sweat to the production. Now for the adrenergic receptors, we have here the beta 1, 2, and 3, and then alpha 1 and 2. Now these receptors are located different or in different regions, and so it's important to know that beta 1 receptors are almost or mostly found in the heart, but also kidneys and adipose tissue. Now when norepinephrine and epinephrine, which also called noradrenaline and adrenaline, have some adrenergic bind to beta 1 and adrenergic receptors. So it actually increases heart rate in the force of heart muscle contraction. It also stimulates the kidneys to release renin, which increases blood pressure. So think of the beta 1 receptors found on your heart and your kidneys and adipose tissue. They actually are gonna lead to increased activity, so it increase heart rate, blood pressure, and the rate of the lipolysis or breakdown of lipids and adipose tissue. Now, beta 2 receptors are here located in the lungs, and there are other sympathetic target organs like the blood vessels serving the heart, liver, and skeletal muscle. Now, it's interesting that beta 2 are actually inhibitory mostly. So when epinephrine and norepinephrine bind to beta 2 in the lungs, it actually causes smooth muscle relaxation. That way, these bronchioles can get wider and increase airflow. When epinephrine and norepinephrine bind with beta 2 on the blood vessels that go to our heart, liver, and skeletal muscle, it also causes the smooth muscle to relax, which causes these blood vessels to dilate. That increases blood flow to the heart, liver, and skeletal muscle, which makes sense during the fight or flight response because your heart needs to get more nutrients to pump harder. And then liver and skeletal muscle are also gonna be involved with personal processing nutrients, and your skeletal muscle is gonna help you get away, run, or fight. Now, beta 3 receptors are located on adipose tissue, and this also stimulates lipolysis by fat cells, so that when epinephrine or norepinephrine bind the beta 3 receptor on adipose, it stimulates the breakdown of fat. That way can release more fatty acids in bloodstream, which is basically just nutrients, and help your cells undergo to fight or flight response. That'll make sense. Now, alpha 1 receptors are located on most sympathetic target organs, especially the blood vessels of your skin, mucosa, abdominal viscera, kidneys, and salivary glands. But if you think about this in terms of alpha 1 are associated with
these organs, but it is important for blood flow to increase in skin mucosa, kidneys, and salivary glands? The answer is no. The effect of alpha-1 receptors actually causes constriction or constriction of blood vessels as well as visceral organ sphincters. The effect of alpha-1 receptors actually causes constriction of blood vessels as well as visceral organ sphincters. So the effects are mostly excitatory here, in the sense that it actually causes smooth muscle blood vessels to constrict, with causes visceral constriction and decreases blood flow to your skin, mucous membranes, abdominal viscera, kidneys, and salivary glands, which makes sense. It also causes the pupillary dilatory muscle to contract, which causes your pupils to dilate and get wider. Now, alpha-2 receptors are located on adrenergic terminals and pancreas. Now, it actually involves negative tendencies or inhibits the release of norepinephrine from nerve terminals. But these alpha-2 receptors in the pancreas inhibit the release of insulin. Insulin is a hormone released by your pancreas that lowers blood sugar. So if epinephrine and norepinephrine interact with alpha-2 receptor in the pancreas, it prevents the hormone that lowers blood sugar, then your blood sugar will gonna remain high during the fight or flight response. And that also makes sense. So to sum it up, these are basically the locations of both adrenergic and cholinergic receptors. So where they are found in the body and the major effects of these receptors. Now let's discuss receptor agonist and antagonist. So an agonist is any drug that binds to a receptor and activates the receptor. So the key word here is activate. So it doesn't matter what the receptor does. If the drugs activate the receptor, then the drug is an agonist. So here is an agonist comes in contact with the receptor and activates the receptor, causing some kind of charge inside of the cell. Because this drug activates the receptor, it is considered an agonist, and that's why it is colored here with green. So in most cases, agonists leaving the binding sites deactivate the receptor. So this is normally what occurs, and we need to remember this. So in some receptors, agonist permanently activates the receptor. So antagonist is obviously the opposite of agonist. It is any drug that binds to a receptor and prevents the activation of the receptor. So here's a competitive antagonist that binds to a receptor at the agonist binding site. The receptor is not activated, the agonist cannot combine and activate the receptor, and so a competitive antagonist is called by its name because it competes with agonist at the agonist binding site. So a competitive antagonist is any pharmacological antagonist that competes with the binding of an agonist at the binding site. So we have here a non-competitive antagonist, which is any pharmacological antagonist that binds to a site on the receptor other than the agonist binding site. So here are non-competitive antagonists that's bound to a site other than the agonist binding site. So when a non-competitive antagonist has bound to the receptor, it essentially deactivates the receptor and prevents agonists from being able to activate the receptor. But we can see that they are not competing for some binding site or for the same binding site. The non-competitive antagonists have its own side where it can deactivate the receptor.
So on the other hand, a chemical antagonist is any drug that binds directly to an agonist and deactivates the agonist.
So here's the chemical antagonist, and instead of binding the receptor, it binds to the agonist. By binding to the agonist is not able to activate the receptor.
So we have here the physiologic antagonist, which refers to any drug or chemical that has an opposite effect, but through a completely different physiological pathways. Like histamine and epinephrine, they are physiologic antagonists. So, anaphylaxis is a severe systematic allergic reaction. Excess histamine released by the body is part of the problem. So, histamine will cause capillary leakage and a collapse of systematic vascular resistance. And if there's enough histamine released into our body, that loss of systematic vascular resistance will cause blood pressure to go zero, which is a shock. And so that's the definition of a medical shock. The collapse of blood pressure. Epinephrine is given to counteract the effect of excess histamine because epinephrine is a vasoconstrictor that raises blood pressure, but they don't do this by competing in the same binding site or interact with each other. They have completely opposite physiologic effects through opposite physiologic pathways. So epinephrine is given to counteract the effect of excess histamine, but they work by completely different receptors and physiologic pathways, as I have said earlier. And so, histamine and epinephrine are physiologic antagonists.